Right, so let's take a look at 6.3 part 2. So yesterday we looked at the two transformations that were shifts, phase shift, vertical shift. Today we're going to look at the stretches. So first thing we're going to look at is what's called the amplitude of a sine or cosine wave. All right, so the amplitude of a sine or cosine wave basically measures how high it goes. Like if you imagine putting a center line right in the middle of the wave, it's the distance from the center line to the top, which should be symmetrical from the center line to the bottom. That's why it's a center line. All right, so that's your amplitude. So the amplitude measures a distance, which means it would have to be what kind of number if it's measuring distance? Yeah?
A positive.
Positive. So whenever we talk about the amplitude of a sine or cosine function, we always use a positive number to describe it. Which I'm going to write down in a second. So both of the stretches, whether it's a vertical stretch or a horizontal stretch, this is the vertical stretch called an amplitude change. They both use multiplication. The difference is going to be, did you multiply by a number outside the sine or cosine function, or did you multiply inside, right next to the x? This is outside. Anything you do outside is always vertical, just like the way we've done it all year. So if I give you a problem and ask you what is the amplitude, it's just the absolute value of the number in front. So you might have a couple problems on the test where you don't have to graph. All I'll do is give you an equation and ask you, what's the amplitude? Just by looking at the equation. Okay, so we'll try. I'm going to write down a couple, and we'll just try to find the amplitude. So let's do. Function and the amplitude. All right, so let's say we had y equals 3 cosine x. What's the amplitude of that? Yeah, 3. All right, how about like y equals 3 sine x? What's the amplitude of that? 3. It doesn't matter if it's sine or cosine. Right. How about y equals -2 cosine x. 2. Now, I'm not saying the negative doesn't do something to the graph. It does. We've learned what negatives do. But if all you're asking about is the amplitude, the negative has no effect on it. Okay? How about that one? What would be the amplitude of that? 1. So this doesn't change the amplitude. The negative does something, but it doesn't. What it does doesn't change the amplitude. How about let's do 2 cosine x plus pi minus 5. What's the amplitude there? Still what? 2. There's other things happening, but they don't affect the amplitude. There's a phase shift, so you're shifting it right, and then you're shifting it down. But that doesn't have anything to do with the amplitude. So some people get a little confused with the idea between the highest value that a function hits and the amplitude. If you had a graph like this, say that's your center line. What's the amplitude there? Yeah? 1. The amplitude is just 1. That's the distance from that center line to the highest or lowest part of the wave. But what's the highest y value that the wave hits? Yep. 3. So the amplitude and the maximum value don't have to be the same, like in that case. Okay. All right, so again, amplitude is always positive, but if you're graphing it, you do have to take into account the negative, which causes a flip. Right? So we'll practice some graphs. So this is when we're stretching or compressing the graph along the y-axis. So out of the two stretches, I think this is the easier one because you're changing the y values. If you're changing the y's, and that's all you do, what stays the same? The x's. And we like when the x's stay the same because the x's are all the fractions with pi. So when you're doing this, you don't have to deal with the x's. Actually, I have some more finding the amplitude. You don't have to write these ones down, but we can just go through them quick. Amplitude there? 3. How about that one? 4/3. There's other stuff like a shift, phase shift, and a vertical shift. The vertical shift would affect the maximum value, but it doesn't affect the amplitude. How about that one? 2. Okay, so those are your amplitudes. Okay. Any questions on those? All right. So how do we actually do a sketch? So you're going to start with those 5 points from the table I gave you yesterday. And we just said all the x's stay the same. So you're going to take all the x's from the table, copy them down. So every problem we do in this part of the section, your x's will be 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, the y's are all going to change. Luckily, your y's are very easy to change because they're all 1, 0s, and negative 1s. So all you have to do is arithmetic with a 1, a 0, or negative 1. And the arithmetic you're going to do is you're going to multiply all the old y values by c. And if I go back for a second, c is just the number in front. Does anybody know why I use c? Like I use c for the vertical stretch. I think I use d for the vertical shift. I mean, vertical doesn't begin with c, but I guess it has a c in it. Yeah.
It's like the order of when you do the shifts.
Yeah. When we get to a problem where we have all 4, this would be the 3rd one that you do. Vertical stretches or reflections, because if you put a negative in front, it's a reflection, so there'd be 2 things at the same time. But stretches and reflections vertically are the last 2, are the 3rd things you do. Shifts were D, because those are the last thing you do. Phase shift, I think I used the letter A, hope I did, because phase shift is always the first thing you do. And then the second thing you do, that's a period change. We haven't done that one yet. Any questions on the 2 steps? So what do you think the effect would be before we do an example of hearing that? If this was your original sound, and that was your new sound, what do you think the difference would be between those 2? Chris? A higher pitch, okay. What else could be different besides having a higher pitch? Yeah?
Could be louder.
Could be louder. So both transformations today are going to be what we just said. One of them will affect pitch, one of them will affect the volume. So if we find that. Right, if we take a look at this, the name of the slider pretty much tells you what it's going to do. But if I drag it to the left, it starts to flatten the wave out, and it's because the volume is decreasing. If I drag it to the right, it starts stretching it, and it would get louder. So if I play it, and pretty much shouldn't hear anything right there, but this program is a little bit off, so you kind of still hear something, but then it gets louder. Okay, so that's basically stretching or compressing vertically, change in volume. All right. So whether you stretch or compress is basically controlled by that number that's in the front. If the number is bigger than 1, it will stretch. If the number is less than 1, it will compress between 0 and 1. And then if it's negative, what did we say earlier? Negative causes the graph to do what? Flip or reflect. With a negative, with the 3, would that cause it to flip vertically or horizontally? Emily?
Vertical.
Yeah, it would be vertical. Remember, the stuff outside the function is always your vertical. The stuff inside, like right next to the x, like if you have parentheses, all the stuff in the parentheses, that's your horizontal. All right, so this is just, there is no vertical reflection here. It's just a vertical stretch by a factor of 3. So Tori, which values stay the same when we do a vertical stretch? X's. So I can copy those down. I forgot the rest of them.
No, you didn't.
I know. But Kathleen, can you remind me what the rest of them are? Pi?
3 pi over 2.
Yep. And 2 pi. So we picked those because they're nicely spaced in degrees. 0, 90, 180, 270, 360. So 5 nicely spaced points. My original values for cosine, we'll put those first. And then we'll fix them because we're going to triple them. Nathan, what are my original y values for cosine?
0. I don't believe it. All right, 0, 1, 0, negative 1, 0.
Those are definitely y values for a different function.
Oh, I don't know.
Those are for sine.
Oh.
So it's still the same numbers, but you start at a different value. Yep.
1, 0, negative 1, 0.
Yes. So those are, oh, I didn't want to put those there. So those are your y values, and those are the originals. Now we're going to take and triple them all. So Madison, if I triple them all, that's what I want to put in the y column. So what would I put?
3. Would that still be 0?
What's 0 times 3?
0.
There you go.
Negative 2. 0. 3.
Yep. And that's it. So it's pretty easy to get. It's pretty easy to get the table because you just have to multiply ones and negative ones and zeros by a number. Okay. Any questions on the table? All right. Now we make our graph. Okay. What I would do is I would label my x's the way we've been doing. Pi over 2, pi, 3 pi over 2, 2 pi. And 0 I don't have to label, but I can. That's the axis. Now, I have to go as high as 3 and as low as negative 3. What you could do is on your y-axis, just change the scale so each tick mark is 3 units. You could just do it that way. Or you could make each tick mark 1 unit if you did something like that. That's fine too. But I'm just going to change the scale so it's like that. And now graph your points. So you've got 3, 0, negative 3, 0, and back to 3. And that's your graph. Now, if the problem said to graph 6 cosine x, I could pretty much use that exact same picture and just do this. Now that's a graph of 6 cosine x. So a lot of my graphs today are going to look the same. The reason is I'm going to change the scale depending on the problem. Because it's a lot easier for me to change the scale because then I can fit the graph in the same space. Otherwise, I need to start drawing things like 6 times as big. I'm going to run out of space. Okay. Or I'm going to have to put tick marks like really, really close together. So if you notice that on your homework that a lot of the graphs are looking the same, it's probably because you're using different scales in each problem. Any questions on that? Okay, so that's a vertical stretch. Again, that would be like a louder sound. What would happen here if sine of x was a sound wave and you did 1/2 sine x, how would you hear that one, Chris?
They become quieter.
Yeah, become quieter. I don't know if it necessarily means if you make the wave half as tall, it's half as loud. Sound is measured in decibels, and I'm not really sure exactly if it's like a directly proportional relationship with the amplitude. But it would be quieter. Right. So Justin, which values are going to stay the same this time?
The y values, the x values.
The x value. What kind, Gabe? What kind of transformation is this again? Is it a phase shift, vertical shift? Can you be a little more specific? Well, like if I just said on a test, tell me the name of this transformation. And your 4 choices are period change, amplitude change, vertical stretch, vertical shift.
Vertical shift.
No, shift is when you have addition or subtraction. So the shifts are what we did yesterday. Right?
Stretch.
What kind of stretch?
Vertical
Yes,
stretch.
that's a vertical stretch. You can also call it an amplitude change. So again, the 4 types are vertical stretch, also known as an amplitude change, horizontal stretch, or compression, which is a period change, horizontal shift, which we call a phase shift, and a vertical shift, which we call a vertical shift. There's no other name for that. All right, so when we're stretching vertically, that affects the y values. X's stay the same. So that's what we start with. And Jacob, what are my original y values for sine?
For sine, 0, 1, 0, -1, and 0.
Yep. So there's my original y's. And Emma, what am I going to do to all of them?
Well, divide by half.
Yeah, I'm going to take half of them. So 0, half, 0, -1/2, 0, and you're done. Okay. Now this is going to look just like the graph of sine x because I'm going to change my scale. Each tick mark on the y-axis is going to represent half a unit. On the x-axis, it's going to be what we always do. And if you're wondering, do I have to label the x-axis? Yes. If you don't label it, I'm going to assume your x-axis is going by ones, because that's what each tick mark usually represents. So if you want your tick marks to go by 90-degree increments, which is what they're doing here, or pi/2 radian increments, you got to label them. Okay. All right, so 0, half, 0, -1/2, 0. So that's the case. I probably should have put the label a little lower, or maybe I should have put it up above the line, but oh well. If you did that on a test, that's fine. I can still read the labels. Okay. Any questions on that one? All right, and let's look at one more, which really isn't an amplitude change, but the way you graph it, the arithmetic still falls under the same category as an amplitude change. Why am I saying that's not an amplitude change? Yeah?
Because the absolute value of -1 is 1.
Yeah, it's like you have a -1 in front. So the amplitude of this is still -1. So my x's are the same. But what am I going to multiply all my y values by? -1. So that's not going to change the amplitude, but what is it going to do to the graph? It's going to flip it which way? Yeah. Vertically. So what was a peak before is now like the trough, the low point, and what was the low point is now the peak. They're all going to switch places. So you'd have 0, -1, 0. Let me write the originals. I can't think. That was sine. Sorry. 1, 0, -1, 0, 1. So now change the sign of all of them. -1, 0, 1, 0, -1. Okay. So instead of this one looking like the kind of that U-shaped part of the wave we get, it's going to be more like an N shape. Okay. It's actually what, if you want it to be specific, it's what we call the concave down portion of the wave. Or I'm sorry, concave up, because it'll open up. So we got, wait, which way is it? No, it's going to open down. I should just draw it and then talk about it. And then, oh, right there. So this part right here, in red, that's concave down. That's what you call that part, because it opens down. This part in green is concave up, and that's also concave up, because it's starting to curve up. If it's concave up, it would hold water. If it's concave down, the water would fall right out. Now I should put some labels on here. So technically I don't have to label my y-axis because I am going by ones this time. Anytime you go by ones, you can leave the labels off. But the other labels I need. That's it. Bless you. Okay, any questions on that one? Okay, so there's your different kinds of amplitude changes, including putting a negative in front, which causes a reflection. All right, the last thing we're going to look at is a period change. So in terms of sound, period change I think is the most interesting one that you can do different things with. And remember that the standard period for sine and cosine is 2 pi. What does that mean? The period is 2 pi. So like if you had to explain to somebody what the period means for a sine and cosine function, how would you explain that? Yeah?
One section that you could copy and paste over is 2 pi long.
Yeah. It's that section that describes the full graph, just like that. That from start to finish is 2 pi units, or 360 degrees. So now what we're going to be doing is we're going to alter that. We might take the graph and, well, maybe if I draw it again. Take something like that and compress it. So don't change the height, but just compress it. Or we could take something, keep the height the same, but stretch it out. So if stretching up and down changed the volume, this is going to change something else. Now we're back on the inside. Anytime you do a transformation on the inside, that's always horizontal. When you multiply, it's a stretch. When you add or subtract, it's a shift. This is multiplication. Tells me it's a stretch. It's in the parentheses. That tells me it's horizontal. So we're just going to be looking at examples where b is greater than 0. If it was less than 0, it would cause a reflection. This would be a horizontal reflection. But for the kind of graphs that we look at, we're just going to focus on b as a positive. Now, there's a number where if you go above this number or below this number, bless you, it'll either start to stretch or compress. Does anyone have an idea of what number is kind of the dividing point between whether your graph stretches or compresses? Yeah?
1.
It's at 1. So let me graph something like sine 4x. What do you think is going to happen there compared to sine of x? Do you think that that's going to stretch out? Or do you think this graph is going to compress? Compress? You think it's going to compress? How about Joe? What do you think?
Yeah, compress.
Compress?
Sure.
Are you just agreeing with Kaya?
Yeah.
Okay. It's probably a good person to agree with because she is right. You might think, oh, well, it's a big number, right? 4 is bigger than 1. Bigger. Stretch is bigger. It doesn't work that way. It does the opposite of what you would expect. In fact, this graph compressed 4 times as much. So if I put the original up, you're going to see 4 cycles in blue for every 1 cycle in red, because it compressed by a factor of 4. And an easy way to see it is just take something like this and just focus on one section. Right there. Count how many red cycles you see, and then count how many blue. There's exactly 4 blue cycles there. All right? So the higher you make this number, like if I made it a 5, it would compress 5 times as much. 20 times as much. The higher you make it, the more compression you get. If I do something like 0.5x or 1/2x, that's going to stretch it. Right? So now in blue, you're going to see something that's been stretched out twice as much. Compared to the red, that's your original. So now for every cycle in red, you're only getting half a cycle in blue. We'll get 1 full cycle in red. Well, the blue part, you've only gone halfway. The closer you make your fraction to 0, the more stretching you get. So 1/5 would stretch it 5 times as much. 1/20, 20 times as much. All right. So you get stretching and compressing. So I already said that. Stretches and compresses on the x-axis. And we just said that. Greater than 1, you get compression. Less than 1, you get stretching. But it'll always be more than 0 because that's what I said earlier. We're not going to look at negatives. Okay, so what do you think that would change in terms of you hearing it? If you stretch or compress a sound wave horizontally. Well, Chuck, what do you think?
It'll like be like the I don't know how to describe it. Like the sound would be like more clear and less clear, I guess.
Okay, so like more or less clear. Well, the clarity is pretty much going to be the same. Like when you stretch or compress it. The only thing that would change clarity, I guess, would be like if that speaker was inside a box and it sounded muffled or something like that. But that part's going to stay the same. Any other guess what will change? Yeah?
That would be the pitch, right?
Yes. It's going to change the frequency of the sound or the pitch. So if we play something at like 1,000 hertz, okay, we hear that, versus if I play something at like 8,000 hertz, you can see it's compressed so much you can't even really draw it. There's just not enough room on the screen. But it's very compressed. Yeah, let's just go right to 10,000. So you get a much higher pitch sound. And eventually, if you keep compressing it enough, now that's about 19.5 kilohertz, or 19,500 hertz. If I play that one, I hear like this little buzzing, but I don't really hear the real sound. Anyone hear the really like extremely high pitch? You hear it?
Yeah, you can. It's like.
Anybody not hear the really high pitched sound? Yeah, if I put it down, you'll know what I mean. Like it would be like this sound. If I bring it down so you can hear it, it would be this sound but like way higher. People hear that one now?
Yeah.
Yeah.
It would be that but even higher. All right. So 16,000. That's when I can't quite hear it. I mean, I hear the speaker I hear the speaker turn on, but I don't hear the sound actually coming out. I think for me around like that, yeah, I definitely hear that one. So that's around 14.6 kilohertz. So that's on the high end. So for humans with like perfect hearing, you can hear up to about 20,000 hertz, which is still pretty low in compared to other animals or fish. Well, no, fish don't have good hearing, but I think dolphins, which are mammals, dolphins, I think they can hear up into 6 figures. So they can hear like that was 20,000. They can hear up over 100,000 hertz. So that's just insanely high pitch. Way more than we could even imagine. Like way more than like a dog whistle or anything like that. And then on the other end, we already kind of played these. We get low pitch sounds. Low pitch sounds, you do hear it, but you also start to feel it. And objects resonate. Different objects vibrate at different frequencies. And if I play that, you could actually hear different objects in the room vibrating. Not sure what they are, but you'll definitely hear them. So I just have to get the right frequency. When I hit it, you'll hear something start vibrating. So let me play this. Might need a little more amplitude. So there's something vibrating at 50 hertz. And what's really weird, at 50 hertz, I don't even really hear the sound here anymore vibrating. I don't know if it's just the way it's echoing, but like 48 and 49 hertz was kind of hurting my ears. It was like really a lot of sound. 50, all of a sudden it was like, it's like the sound went away for me. Like that's extremely loud for me. I can barely hear that standing right here. But it's vibrating something. So different, I think there's more too. So 53 hertz, got something else vibrating. Glass vibrates at usually higher frequencies. It's like if you've ever seen like somebody sing and they like break a glass, you can do that. The hard part is you have to sing at exactly the note that the glass resonates at, and you have to hold that note. You can't change it because just changing to 53 to 50 hertz, I got something different vibrating. So you got to have just the right frequency, and it has to be very loud. And every piece of glass is different. So like one wine glass would be different from another one. The glass panes in the windows probably, I don't think those would be able to resonate as well because they're held in. It's like they're held on all sides. So it kind of prevents the glass from vibrating. But if you have just like a regular like wine glass and like you flick it with your finger and you hear that that sound that it makes, that's the sound that it resonates at. So if you had some way of figuring out exactly what that sound was, which if you have something like this, this is an oscilloscope. And an oscilloscope will tell you the frequency of what it's hearing. So if I talk normally, I'm using all different frequencies in my voice, so there isn't really a clear sine wave. But if I whistle, so if I do something like, you could see the sine wave. It was kind of fluctuating a little because I couldn't keep it perfect.
You try singing into it.
Like hold it down.
What's that? Yeah. If somebody could sing and hold like a perfect note, one single note, you would see a perfect sine wave.
Could you try that?
See? No, I don't want that. But this is the thing that main frequency. So if I whistle, it'll tell you like what frequency I'm whistling at. Right now it's jumping all around because my voice is, it's thousands of frequencies you're hearing at the same time, which is what makes my voice my voice. So if I whistle, you should see pretty much just one frequency not jumping around and kind of a spike, probably around 2000 hertz. It's probably about what my whistle is. So let me try it again. Let's see. So it's about 1.3 kilohertz. So if I play 1300 hertz, that should sound pretty close to what I was whistling at. Let's see. Pretty close. That's the frequency I was whistling at. It obviously sounds a little different because that's an electronic version of the frequency, where I'm not a robot. I'm not electronic. I'm human. So that's why when you have different instruments, like you could play a certain note. They don't call them frequencies on like a piano. Usually they call them notes. And you could play like middle C on a piano, then you could play middle C on a guitar. And this might say exactly the same frequency number, but I think most people would hear the difference because just there's characteristics that make something sound like a guitar versus a piano. They could be the exact same mathematical frequency, but it just sounds different because it's made from a different instrument. So that's an oscilloscope. So they used to have like boxes where you could do this. Now you can pretty much get one for a computer. And as long as you have a microphone, which I do, you can pick up different frequencies and all kinds of stuff. You can also generate frequencies with it too, but I just wanted to show you that. All right. So this kind of thing, we're stretching and compressing on the x-axis, which means, unfortunately, when we get into graphing, we have to deal with the x's again. So we're going to have to deal with the pi's and the W's. So one question I'm going to ask you, kind of like the amplitude, it's a non-graphing question. It's just find the period of sine or cosine. So it was 2 pi, but if you stretch or compress it, it's not anymore. I want to know what is it now that you stretched it or compressed it. So this is the formula that you use. To find the new period of a sine or a cosine function, you take the original period and you divide by b. B is the number, right here. B is the number in front of x. Okay, so let's look at some examples that these are not graphing, just finding the period. Okay, so set it up. So I'm going to have a fraction. What always goes in the top of the fraction when you're finding the new period? This never changes. Blake?
2 pi.
2 pi. Now, what goes in the bottom changes depending on the problem. It's b. What's Emily? What's b in this case?
Or no, sorry. It would be 2.
2. Yeah. So b is the number in front of x. And in this case, it's 2 pi over 2, or pi. So what that means is your graph is going to do a full cycle. It's going to do that between 0 and pi, where before it had to go to 2 pi. So what you actually did is you compressed this graph twice as much. Be a higher frequency sound. Right, let's look at this one. Cosine 1/3 x. So t equals. Joe, what goes in the top?
2 pi.
2 pi. And Haley, what goes in the bottom?
1/3.
1/3. What's 2 pi divided by 1/3? Yep. 6 pi. So what you've done this time is you've stretched the graph out. Now you've got to go all the way from 0 to 6 pi before the graph is going to finish a cycle. So you've stretched it 3 times what it was. It's 2 pi, now it's 6 pi. All right, let's look at this one. Okay, what would be the period here if it was 2 pi over pi? 2. So this would actually be one where the your x-axis labels would be very nice. Okay, the period, you could label your x-axis, you could go by ones, you could go by ones. You wouldn't even need pi in them, right? Because the pi ends up canceling. And how about, what would the period be here? As a fraction. We never write it as a decimal. Okay? 2 pi over 3. You got to put that 2 pi in the top. Don't say the period is 3. That's just the denominator. So there's a vertical shift, and there's also a vertical stretch, but those don't have any effect on the period. Now, what if I asked for the amplitude there? What's the amplitude in D? Yeah? 2. So you just have to know what number to focus on when you're looking for period or amplitude. All right. So this time, all the y's stay the same. Okay, again, unfortunately, those are the easy ones. We don't get to work with them this time. So copy the y's down from your original table. Now, your new x's. There's a few different ways to get the new x's. But the way I'm going to show you is a way that's going to work when we do more complicated problems. So I'm showing you a way that is good when we start extending this to multiple transformations in the same problem. It's not always the fastest way to do it if you don't have multiple transformations, but it does work. And the way I'm explaining it is to take all the original x values and divide them by b. So whatever the number is in front of x, take your 0, your pi over 2, your pi, your 3 pi over 2, and 2 pi, and divide every one of those by b. What that means you usually end up with doing it this way is fractions over fractions. So not always the fastest way to do it. You might be able to figure out other ways to do this. But we'll go with that for now because it'll work for us tomorrow. Okay. Any questions on those two steps? All right, so let's look at this one. Y equals sine 1/2 x. Okay, first step, can somebody tell me, now that we've learned all the transformations, phase shift, vertical shift, amplitude change, period change, which one of the 4 is it, and why? Yep.
It's a period change.
Yep, it is a period change.
Because it's like with the x. The
And
number.
the number is with the x, and what are you doing with that number and the x?
We're, stretching.
So I agree, it is going to cause a stretch, but what arithmetic operation with the 1/2 and the x?
Oh, and multiplication.
Multiplication. So whenever you have multiplication, it's always a stretch. When it's inside, it's a horizontal. When it's outside, it's a vertical. All right. So that means all my y values stay the same because I'm going to do something horizontally. So we're not going to mess with the vertical stuff. Yeah.
And then give you the one value.
Sure.
0, 1, 0, -1, 0.
Okay. So there's my y values. Again, on a test, I'd probably give you 1 point for each one of those you get right. Usually, I think that's what it usually works out to. And now let's put my original x's on the outside. 0, pi over 2, pi, 3 pi over 2, 2 pi. Now, what are we going to divide all those by? A half. But if we want to think of it a different way, we can avoid fractions over fractions, because dividing by half is the same as multiplying by what?
2.
2. So really, you're doubling everything. And that's, for me, that's an easier way to think about it. So you're going to double that, double that, double that, that, and that. And if you see a nice pattern, that probably means you did it right. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. Any questions on how I got those from doubling the originals? Okay, so there's my table. This time I'm going to label my x-axis. I'm not going to use pi over 2 pi, 3 pi over 2, and 2 pi, because I got to go a lot higher. I got to go all the way to 4 pi, this stretched. So I'm going to go 0, pi, 2 pi, 3 pi, 4 pi. Each tick mark represents pi radians. If you want to think of it in degrees, it's 180 degrees. 1 to -1, that's going to work fine for my y's. So just do that. So 0, 1, 0, -1, back to 0. And it doesn't really look like that graph stretched, because if you look at it, you're like, it looks the same size as everything we've always done. Why? Why doesn't it look like my graph is huge on the screen? Yeah?
You changed the scale.
I changed the scale. That's why. Okay. Questions on that one? All right, let's look at a so let's look at a cosine, and this time it's a number bigger than 1 in front. So this is going to cause the opposite of the last problem. It's going to cause a compression. Okay, Gabe, what are my y values for cosine?
1, 0, -1, 0, 1.
Yeah. And remember, we're only sketching one cycle. So are there other y values than this? Sure, I could make more. If I wanted to do another cycle, I'd put another 0, -1, 0, 1. But I'm stopping here because I only want to do one cycle. Okay, and now my x's. 0, pi over 2, pi, 3 pi over 2, 2 pi. Kaylee, what am I dividing all my x's by here?
By 2.
I'm dividing them by 2, which is the same as what?
Multiplying it by 1/2.
Yeah, we're going to take half of all of them. So let's start with 0. What's half of 0?
0.
0. What's half of pi over 2?
Pi over 4.
Pi over 4. What's half of pi? Yeah,
Pi over 2.
just half of pi. Yeah, just pi over 2. Half of 3 pi over 2. Blake?
3 pi over 4.
3 pi over 4. And the last one, half of 2 pi, is 1 pi. And if you look at it and you're like, I don't see a pattern, it's because we don't have everything with the same denominator. If you did that, you'd see a pattern. 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. The next one would be 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. And that's it. That's your table. Okay, so let's label our axes. Okay, if I look at these in degrees, that's 0, 45, 90, 135, 180. They're all 45 apart, and I didn't skip over my axis. So I'm not going to have to skip anything here. So pi over 4, pi over 2, 3 pi over 4, and pi. So 1, 0, -1, 0, 1. It's a little off, but it's not that bad. And there's your sketch. Questions on that one? All right, so the last one we'll look at, looks like it could be really bad because of that number in front, but remember what happened when I said find the period, and we had something with pi in front. It ended up just disappearing. So let's make our table. Y values, we just did those in the last problem. Let's just copy them down again. Now, how about Emma? What am I going to multiply, or what am I going to divide all my x values by? I'm going to divide them by pi over 3, which is the same as multiplying them by what? Yeah, let's just multiply everything by 3 over pi. Probably only going to have to do it a couple times, and you'll see a pattern. Well, I don't know if you've noticed yet, but if you haven't done a phase shift, which would move the x values left and right, your first x value is always 0, because no matter what you multiply or divide 0 by, it's 0. Now, if you do a phase shift, that's not true. That could change things. But as long as you got a 0, it'll stay as a 0. Pi over 2. We're going to multiply by 3 over pi. And all you get is 3 halves. Let's do one more, and then I think that'll be good. So pi, you just get 3. You're going up by 1.5 each time. So what's the next one?
4.5.
4.5 and 6. So you could label your x-axis by 1s. I need one more. If I want to go by 1s. I could go by 2s if I was running out of space, but I had enough space. So 1 and -1. And 1, 2, 3, 4, 5, 6. This is the only problem we've done all week, that if you forgot your labels, you wouldn't lose any points. Because I would assume you're going by 1s, and that's probably what you should go by here. All right? Even though we've got some halves, that's not an awful number to graph. So you got 0, 1, 1.5, 0, 3, -1, 4.5, you're back at 0, and 6, 1. So what's the normal period again if you don't stretch or compress it? 2 pi. And what's 2 times pi? Okay, like as a decimal.
6.28.
It's about 6.28. So normally a graph has to go all the way to 6.28 to do a full cycle. This graph had to go to 6. So it compressed a very small amount. It's like 0.28 shorter. It's very, very, very small compression. And that's because this number is very, very close to 1. Pi divided by 3. You'll figure out what that is. It's like 1.04, 1.05. You just barely multiplied by a number bigger than 1. So not much compression. Good. Any questions on that? So the last part of what we have is looking at the multiple transformations. Okay, the same problem. We'll look at that tomorrow. And then we'll also solve a few equations. And we'll finish up on Thursday with graphs of other trig functions. Okay, so that's the homework for tonight. Again, it's on a worksheet. But if you lose the worksheet or something happens, just go to the end of the video and there's all the problems.